Hello and welcome. My name is Engineer Virura Pogo. I'm a civil engineer with 10 years experience in oil and gas, highway and structural engineering. I'm registered with the Council for the Regulation of Engineering in Nigeria, as well as the Project Management Institute, PMI, in the United States of America. I also possess certifications as a certified associate with AutoCAD and AutoCAD Civil 3D. It has become increasingly obvious the fact that several young civil and structural engineers try to enter into the energy, petrochemical, and oil and gas industry, but often find themselves not having the requisite knowledge, often due to the specialist nature of these industries. Some reasons which I believe is to blame are: 1. This aspect of structural engineering is not taught at undergraduate level. 2. This aspect of structural engineering is a bit complex compared to first degree subjects. 3. A structural engineer needs to have experience and exposure in this field in order to understand the parameters during design and construction. 4. Most of the available information are trade secrets. And 5. There has not been much literature on this subject. Onshore structural design is the aspect of structural engineering that deals with the design of energy processing facilities, petrochemical plants, and oil and gas industry facilities. Onshore structures, as opposed to offshore structures, are structures which are domiciled on land and are a distance from the shoreline or the ocean. This nomenclature has been given to differentiate these specialist structures from general structures on land, for example, general buildings and roads, which are also on land. In 2016, a book was written by Dr. Mohamed El-Ridi. The title of the book is Onshore Structural Design Calculations. Dr. El-Ridi is a structural engineering consultant and has offered his services to several major players in the oil industry. For example, International Egyptian Oil Company, Aramco, and Petronas. As a matter of fact, I have a copy of his book right here with me. This 430-page book covers most of everything a young civil engineer will need to understand about onshore structural design. In a nutshell, onshore structural design involves considerations as pertaining to industrial steel structural frames, equipment and storage facilities, vibrating equipment support, pile foundations, soil investigation, assessment of industrial steel structural frames, and blast resistant estimation of structures. In general, there are 7 different facility features that need to be designed by a structural engineer. Number 1 is the pipe rack. Number 2 are the supports for horizontal vessels. Number 3 are the supports for vertical vessels. Number 4 are pipe bridges and supports. Number 5 are storage tanks. Number 6 are industrial steel structural frames. And number 7 are piles and other types of foundation. Onshore structural design is intricate, so structural engineers need to have a lot of experience while working in this field. They will also need to consult past projects. They will need to get parameters from both internal and external stakeholders. They will also need to consult a lot of codes and instruction manuals. For example, let's say a structural engineer wants to design the support of a vertical vessel. They will first of all need to get information from the client. They will need to consult past projects to know what has worked and what has not worked. They will then need to get data sheets from the manufacturers. And this data sheet can contain information such as the weight of the vertical vessel, the physical characteristics of the vessel, the dimensions, the possible wind load that will be coming onto the vertical vessel, as well as the bottom plate dimensions of the support of that vertical vessel. These are key information that the structural engineer uses as an input to commence his own design calculations. So, to make things easier for young civil engineers, I've provided some steps that will help in the design of each of those 7 facility features. I'll be starting with the first one, which is the pipe rack. So now we will be considering the steps to design each facility feature of industrial infrastructure. First of all, you have the pipe rack. Pipe racks are basic facility feature of industrial facilities as they support pipes which transport products and other fluids from one end to a distant location. They also support cable trays and other such utilities. Some parameters considered in the design are the sizes of the pipes to be carried, the total length of utilities to be supported, the maximum possible span of pipes and cable trays between supports, the maximum deflection and movement of the structure and parts. We all understand that pipe racks are used to support pipes which are usually carrying delicate products, and if there is excessive movement beyond the allowable limits, there could be rupture of these pipes, which could end up leading to a major accident or hazard on site. So all these parameters, it's very key for them to be considered during the design. The following are the steps to take while designing the pipe rack. 1. Obtaining of the layout of the pipe rack from the project engineering managers or the clients. 2. Configuration of the structure. This involves selecting the span-to-span distance of each frame cross-section along the length of the pipe rack system. The maximum distance between each frame should be determined so as not to have pipes which are excessively spanned and then they will begin to sag. 3. Estimation of loading from pipes, cable tray, and other equipment attached on the beams and other supports. 4. Determination of all loads in accordance with relevant loads. Aside the pipe loading, you need to get the dead loads for all the other members. Also, you also need to get the test dead load of the pipes and the operating dead loads. This involves having an idea of the fluid that will be used for test and that will be used during operation. You also need to get the live loads, wind load, and earthquake loads. The earthquake load is important in case there is such a tremor in the future of the project, so that the adverse effect does not bring the whole pipe rack system into jeopardy. 5. placement of loads on the structure, and generation of load combination. This load combination has been recommended by the different codes of practice as they help to identify and estimate the most adverse combinations that will give you the highest loading on the structure. 6. Analyzing the structure and designing the members. So you will see here some pictures. The first picture you will see here is the general layout of the pipe rack configuration from STAAD Pro. You can see the pipe rack frames and the distances between each of the frames. Also attached to the pipe rack system is an open frame structure. This open frame structure is what houses the steps that give access to the top of the pipe rack. In the next picture, you will see some load arrangements for dead load for the open frame structure. Next, you have the wind load, which acts upon the open frame structure as well as the pipe rack structure. When these have been analyzed and the support reactions have been obtained, support reactions and moments have been obtained, those points of support are then transferred to STAAD foundation. The last photo you see there are the points of support for the pipe rack and the open frame structure. Those points are then designed for the isolated footings that support the pipe rack and open frame structure. And because the soil bearing can handle it, we have used here isolated footings for the foundation support. The second facility feature we'll be designing is the horizontal vessel. In this case, as a structural engineer, when you work on horizontal vessels, your concern is the support of these vessels, not the vessel itself. Most times the vessel is obtained from an external manufacturer. Horizontal vessels are structures which contain and usually process fluids and span more in the horizontal direction. Some parameters considered in the design of the footing of the supports are the sizes of the vessel to be carried, the likely purpose of the vessel. For example, it could be an heat exchanger or an oil separator. The manner in which the support of an heat exchanger moves is different from how an oil separator might move due to, for example, the bundle pull effect, which you will learn later. Another parameter to consider is properties of the selected horizontal vessel. Such properties as the center to center distance of the supports, the positions of the bolt points on the saddle, that is the supporting plate of the horizontal vessel. The following are the steps to be taken while designing the foundation of a horizontal vessel. 1. Obtaining of the template of the saddle, which is the supporting plate connected to the horizontal vessel, and other dimensions of the horizontal vessel from the manufacturer. 2. Configuration of the footing positions. 3. Estimation of loading from the vessels, pipes, and other equipments which are attached. 4. Determination of other loads in accordance with relevant codes. For example, the dead loads, the test dead load or operating dead load, live load, wind load, earthquake load, thermal load, bundle pull load. 5. Designing the steel slide plates. Designing the pier after doing sizing. Footing sizing and design. 6. Designing of the footing based on different load cases generated to obtain the most adverse footing condition and factor of safety. For a horizontal vessel, the number of calculations and load cases to be considered may be large due to the different conditions and the different nature of the supports. So the calculation may be more involved. So you also see here, I've put in pictures of design of footing from STAAD Foundation. So after you've gotten the basic information like the distances, the parameters, the characteristics of the horizontal vessel, you've also done preliminary calculation of the sizing up to the point of the plates on top of the pier, and probably also the size of the piers. Once you have gotten those information, the next thing is to open your STAAD Foundation application and plug in those values. Those values will then help you to calculate the footing and to also design the footing that supports the horizontal vessel. The next feature to be designed is the vertical vessel. Vertical vessels are structures which contain and usually process fluids and span more in the vertical direction. They could also accommodate traffic. When I say accommodate traffic, probably there could be connections of platforms around it to allow people or allow for certain forms of inspection. Also, there are cases where you have steel structural frames that are surrounding the vertical vessel. So people are able to access different levels of the vertical vessel for whatever purpose. Some parameters considered in the design of the footing supports for these vertical vessels are the sizes of the vessel to be carried, the likely purpose of the vessel, properties of the selected vertical vessel. Just as we have for horizontal vessels, vertical vessels are also supplied by the manufacturer, and they provide the data sheet of those vessels. So those information from the data sheet is what the structural engineer takes as his own input to commence his own calculations. The following are the steps to take while designing the foundation of a vertical vessel. 1. Obtaining of the template dimensions of the bottom plate support of the vertical vessel from the manufacturer. 2. Selection of footing shape. 3. Estimation of loading from the vessels, pipes and other equipment attached. 4. Determination of other loads in accordance with relevant codes. Again, you also have dead loads, including those from the test and the operating fluid. You have live load, you have wind load, you have earthquake load, and thermal load. 5. Designing the pedestal, footing, or other type of foundation. 6. Designing of footing based on different load cases generated to obtain the most adverse footing condition and factor of safety. So you will see here I've also put up a picture of a vertical vessel foundation being designed by STAAD Foundation. Like the other case for horizontal vessels, there are several parameters that you plug into the application before you commence your design. So most likely the calculations by hand you will need to do is to obtain the initial loads, the diameter of the bolts that are being installed, most of which come from the data sheet of the manufacturer of the vessel. Then with some preliminary calculations that you have done, you'll be able to go ahead and use the software to design the footing of the vertical vessel. Another facility feature to be designed is the storage tank. For the purpose of this video and scope, storage tanks are large, usually cylindrical above-ground tanks made of metal or concrete for the storage of fluids. They also accommodate as attachments structures which allow for human traffic. These storage tanks, as opposed to how you have the vertical vessels and the horizontal vessels, storage tanks are actually designed completely by structural engineers. The metal plates to be used and their sizes are designed by the structural engineer, as opposed to all those other vessels which are supplied by the manufacturer. Some parameters considered in the design of storage tank and foundation are the required capacity of storage, the purpose of the storage tank, overfill and height characteristics of the tank. Some of these parameters will be provided by the client who require some services to be rendered. So they will tell you what need they have to be satisfied. The following are the steps to take while designing the tank body and the foundation. 1. Obtaining of the capacity and overfill level of the tank. 2. Selection of the type of roof. For example, for storage tanks, the kind of roof that will be used are of different types. There are fixed roofs and there are floating roofs. It all depends on the kind of product that is being stored and some other reasons that you select a particular kind of roof. 3. Determination of thickness of the shell. The shell is the body and the roof. 4. Estimation of loading from the stored fluid. 5. Determination of other loads in accordance with relevant codes. Again, you have dead loads, live load, wind load, earthquake load, thermal load. 6. Designing of the bottom plate thickness. 7. Design of the soil bearing of the bottom of the tank. Designing of the tank wall supporting beam and other types of foundation support. In most cases for a storage tank, the outer edge closest to the wall of the tank and a little segment into the tank is supported by what you call a ring beam. This ring beam goes all around the bottom wall of the storage tank. Every other inner part of the storage tank is supported by the ground. So the stability of the ground and soil bearing of that area is designed for. So you will see here I've also included pictures of a storage tank foundation that has been designed using STAAD foundation. So as before, you will need to do the previous calculations of all the loads, the moments, the thickness of the bottom plates, and all the different sections and loadings. After you have done that, you plug in these values into the STAAD foundation application. Also, you can see here that it also provides an opportunity for you to specify the thickness of the concrete slab below the bottom plate of the tank. Also, it gives you thickness of compacted granular fill. So this thickness will have to be specified in the application, because from there you'll be able to calculate based on the soil bearing capacity of the location, including these materials that have been added and compacted, to know whether it sufficiently supports the storage tank. So in all, I've discussed 4 basic facility features that are designed for. Firstly, I discussed the pipe rack. Secondly, I talked about horizontal vessels. Thirdly, I spoke about vertical vessels. Number 4, I just spoke about storage tanks. These are the basic features in this kind of industrial facilities. All the other things you will need to consider are various checks, confirmation to ascertain that these features will work throughout the design life. For example, when you are doing blast resistance checks, you are doing those blast resistance checks on these particular facilities that have just been designed and constructed. So I've provided here the steps for the design of 4 of the 7 facility features. The complete steps for all 7 facility features, along with other information, are available in the book titled Onshore Structural Design, Step-by-Step Calculations, written by Engineer Apogo. This book simplifies everything that has been done by Dr. Eridi in his own book, Onshore Structural Design Calculations. This step-by-step calculation book also contains step-by-step references to codes and instructions. It also has calculations side by side for those done by hand and those done with computer software. The 2 computer softwares which have been used are STAAD Pro and STAAD Foundation. Those 2 applications are very helpful as they help to simplify what has been done by hand and also provides a check to confirm that what you have done by hand is correct, or also to help you with preliminary sizing of probably your foundation or some other properties of the structure. So I've provided the link for both of these books in the write-up below. So until next time, keep learning.